Okay, good afternoon. I think you hear me well now. I'm Mojdeh Pajouh. I'm Research Assistant Professor at Midwest Roadside Safety Facility. And we are a research center under NTC, Nebraska Transportation Center. And today, me and Brandon, my colleague, will present some of our projects so you learn about the basics of the transportation safety and types of the projects that we work on and the opportunities that there are in this field. First, I would like to show you our crash testing, which is close to the Lincoln Airport. We are one of the very few facilities that we have this full-scale crash testing. And I'm showing you some of that. In office, faculty, students, technicians, engineers, we all do the design and development in the office. And after crash test, we get the data to analyze that. Our mission and goal is first to improve the transportation safety along highways and roadways. Automotive people, they try to keep the vehicles on a street. Our job is that if for any reason the driver run off the road and hits the roadside safety, how we can save them. So that's the part that we do the design. And interestingly, you see that how geotech, transportation, structural people, they go to make the roads safe. In other words, we're gonna reduce the injuries and fatalities when the accidents happen. So we know that some of the accidents we cannot avoid them. So how we save the driver and passengers when they hit those barriers. Increase driver and spectator safety in motorsports. In NASCAR, you see that there are high speed and there is a good chance that they hit the barrier. And lastly, mitigate the threats for critical government facilities. There might be some attacks to the facilities, and we can design those barriers around that so they can keep those attacking vehicles away from the facilities. Here are some of the research tools that we use. First, material characterization at a small scale. In laboratory, we look at different material properties, soil, steel, concrete, wood, any material that is involved in the crash test. After that, we go to the component level testing. Before jumping into the full-scale crash test, because it's so expensive, we only have one shot. Before that, we run several component level to check the connection, to check every part. And if you look at the right part, you see there is a bogie. It is a surrogate vehicle. It does not get damaged. We can run that several times to learn about the impact behavior of different parts, and it's less expensive. So we run it several times with a different post, with a different soil to make sure everything works before getting to the full-scale crash test. What we do is working. You see that in the past 45 years, although we know that the vehicles traveling on the roadways, they are increasing, but there is an apparent decline in the fatalities. So what we are doing, and it's not just us, automotive research team also do their job. We try to have our roads safer. All of the crash testing and the community, we use one manual, and that is called MASH, which is Manual for Assessing Safety Hardware. We need to be consistent. We all should have some setup, design, and evaluation criteria. And every 5 or 6 years, we have to change that, and we have to update this because the vehicle fleet is changing. Driver behavior is changing, the size and the mass of the vehicles are changing, so we have to update our criteria. These are the MASH test vehicles. We have 6 test levels, from 1 to 6. And in each of the test level, we test a number of them. For 1 and 2, it's for low volume roads. And for most of the highways, we should do the small car and the pickup truck. For Tier 4, we should do a small car, pickup truck, and this SUT, single unit truck. And I have a question for you. If we have a barrier that can pass this, why do we have to run tests with the small car? We know that the load that goes to the barrier is a function of the size of the car, the mass, and the velocity. If the velocity is the same, is there any barrier, guardrail, concrete barrier, or bridge rail that can pass this but cannot pass the small car? Yeah?
Would it be too stiff for the small car and too much of a short stop?
That's one of the reasons. Any other reason?
The guardrail may be too high, so the car can just fly off.
Yes, exactly. These cars, the geometry is smaller, okay, and the stiffer is less than the pickup truck. So one of the criteria is that occupants should be safe in the car. We run the small car because it can get stuck under the guardrail. However, with the pickup truck, you don't have this issue. With the pickup truck, the CG is higher. There is a higher chance that it rolls over, which for a small car is stable. There is a less chance for the small car, so there is no way that we can tell before running the test that which one is more critical. The same thing for the trucks. We run tests with different speed. As I said, for the rural areas, for the low volume, we go with 31 and 44 miles per hour and 25 degrees. You know that if the car impacts that at 90 degrees more critical, why do we test at 25 degrees?
Yeah.
Yes.
Do it depends on like the weight of the car too though? Like,
Yes, it's more common. We don't only crash test the very most critical one. We also see that if it's common. If you are on the roadway, there is a higher chance that you hit the guardrail between 0 to 25 rather than 90 degrees. Only for security engineering, for attacking cars, that's the place that the barriers should be for 90 degrees. Here I'm showing some of our barriers and some of our crash tests. On the left side, you see the bridge rail. This time, when you drive over the bridge, look at the bridge rail type. If it's concrete, if it is guardrail, if it is mounted on the top of the slab, or it is mounted to the side of the bridge. If it hits the bridge rail, that load has to go to the bridge deck. So that's the time that the structural people should account for that load when they design the bridge, if there is a bridge rail on that. In the middle, you see the single slope barrier. You have seen single slope or vertical, and also there are some F shape or New Jersey shape. One of the reasons that we don't do the vertical, which in order to, you see when it's a slope, the car has a higher chance to climb over that and roll over. The best way to avoid that is to have to vertical, but we don't do the vertical. Or we try to avoiding that because when it's vertical and you hit that, the acceleration that the occupant feels is higher. Our body can take up to 20 Gs. So at the crash test and in our simulation, we calculate that and make sure that the occupant does not feel more than 20 Gs. This is occupant safety criteria. Here I'm showing some of our project. One is transition between guardrail and concrete. We need a transition between them because the stiffness of these two systems are different. When you have two systems with a different stiffness, you have to have a smooth transition between them. Otherwise, you're gonna have that catastrophic contact. And after designing that and doing simulation with LS-DYNA, which is one of the advanced computational tools that we have, we run the crash test, and both of them with the small car and with the pickup truck, they pass this MASH criteria. We don't only work on the existing, some of our team members, they work on innovating new barriers with the new material. This is one of the energy absorbing resorbable barrier, which I'm going to show you. This is the simulation, and here you have the crash test. The deflection of this is much less than the guardrail, and the energy absorbing system that is embedded into that, the performance is much better than the guardrail, but of course it's more expensive, so you don't see that much common on the roadways.
Is there a difference between, you know, how electric vehicles are becoming more popular year by year? Is there a different testing between, I guess, gasoline cars and electric cars?
Yeah, that's a good question. We are now working, we got model for Tesla, for example. We are working on that because electric vehicles are heavier.
Yeah.
The CG is down because of the battery under that. So that can impact how it interacts now with the barrier. We have to first, and we are doing this research. It's good that like they say that 10 years or 20 years from now that we see all electric vehicles, we have some time to do research. And that's right, we need to update our barriers. If it doesn't work, then we have to update the guardrail, for example, or concrete barriers. These are heavy concrete bridge rails and barriers, and when we have trucks, then we have to have a taller barriers. And you know what? Because of the rollover. We have guardrail on a slope, and then bridge rail, the guardrail, and you should see that lots of research are doing on these guardrails. The rail, the blockout, the post, what should be the soil, the embedment in soil, and all of them can impact how the driver and the passenger experience that accident. We have cameras now on the car, and we have dummy in our crash test. It's not instrumented, so we don't have the velocity or acceleration that like every tissue of that dummy feels that, but that's another level which we like to go there, to have instrumented dummy in the crash test so that we can see the injury and what happens to the occupant. For now, we can get the velocity and acceleration. Here is one of our great projects that we had with crash pushing. These concrete barriers or guardrails, you cannot leave the end open because a car can exactly go through that. So you need to have some treatment for the end of those guardrail or concrete barrier. And you see that if it works well, it can stop the car within a specific distance through energy absorbing mechanism. This is one of the very tall 72-inch barrier, the concrete barrier that we had, and that's the heaviest truck. At the beginning, it was redirected well. Okay, at the end, the splash of the water in the tank made this roll over. And we are now looking into that, and we believe that the barrier did its job. After that, we should make sure that the splash of the water or gas or anything that doesn't make this roll over. Cars are okay to roll up to 75 degrees. After that, it's fake. And here is the other project for security engineering. And you see the barriers should be stronger. For this one, we don't care about the occupant. Okay, we only want the vehicle not to passing some certain distance. And you see what's the difference between transportation safety, which our priority is occupant safety, or keeping the car on the deck, on the bridge, not to roll over. However, for security engineering, we just try to keep or slow them down. These are the two applications, and from now on, when you are on the roadway, look at the barriers and see how they are designed, and see what structural elements that you can think about and how you can improve this. And now I pass that to my colleagues, and later on we will be here for a Q&A.
All right, so I'm going to start off talking about our safer barrier. That stands for Steel and Foam Energy Reduction Barrier. So basically, you can tell by this picture, this barrier was made to reduce race car driver injury. How many of us have seen a really nasty race car accident where the car just goes right into the wall and parts just break everywhere? Yeah, I think we've all pretty well seen one of those. So these accidents typically occur between 120 and 150 miles per hour at 20 to 25 degrees. So this barrier was made to reduce deflections and decelerations. And this particular design it's modular, so that makes it really easy to design, and if a part gets broken, it's really easy to replace. It's also resilient. So if you're in a race, one section gets impacted, it can be impacted again. You can't stop a race for one accident. You can slow it down for a little bit, but you need the barrier to be able to be hit again after an initial hit. So on the bottom left, that's a baseline test. That's a car hitting a concrete wall at 136 miles per hour. Then on the right, you see the safer barrier, pretty similar speeds and impact angles. You can see a lot of debris, just a pointer. Either way, you can see a lot of debris kicking off of the red vehicle, whereas with the gray vehicle hitting the barrier, there's not nearly as much. And that kind of just goes to show that this barrier is helping. You can also see how much damage the vehicle takes on the front passenger side corner as it hits the concrete barrier versus the one that hits the safer barrier. All right, now we'll move on to single post sign support systems, which is a fancy way of saying sign. Sign's got to be easy to figure out, right? Well, no, that's not true at all. So this particular system incorporates a slip base. So a slip base is made so as soon as a vehicle impacts it, the bottom of the sign just kind of breaks away freely. The post doesn't really wrap around the front of the vehicle or anything, it just breaks away. So this particular system, there was a 4-inch under diameter post or sign support with a 4-foot by 4-foot sign post or sign panel. And Mojdeh talked about the test levels. So we tested this to 361, 362. That's a 62 mile per hour test with the small car and the pickup truck. We impacted the sign, rotated at 25 degrees to kind of maximize the interaction of the sign panel and those sign brackets with the windshield or window and the roof. And we also impacted these signs at the quarter point of the vehicle. So if this is the hood of the vehicle, we impacted kind of right there. So top left is the small car and the pickup trucks on the top right. You can see that the sign kind of rotates down and backwards. Oh, video stopped. But either way, so in the top left, the sign rotated backwards and penetrated through the back window, and that's a fail. There could be no penetration into the occupant compartment, even if it's all the way to the back window. So the top right, with the pickup truck, the sign just kind of molds around the intersection where the windshield meets the roof, and the sign brackets kind of just stay away from the roof and the windshield. So that one actually passed. Another thing to note is after those signs are hit, they get really high up in the air. Those go really high in some cases, and that causes a lot of concern for traffic traffic going either way. Maybe a vehicle following these, so that is a concern. So because this was one system and it failed the small car test, this system failed. So we got to come up with a retrofit. So what we did was we added 10 pounds of mass at the top of the signpost, and we raised the post 1.5 feet. So on the bottom, we did computer simulations before we ran any full-scale tests. And you can see it, upper left video, stop again. So in the bottom left with the small car, the sign just barely touches the trunk, so that's good. And with the pickup truck in the simulation and in the video, it does impact the roof, but it's not enough to violate criteria. So this is a safe system, so these both passed. Breakaway luminaire supports, and again, light poles. So again, sounds easy, right? Well, not necessarily. So for this study, which Mojdeh is in charge of, it uses a transformer base, the most common transformer base in the fleet. There were 4 cases for evaluating the 3 test levels. Short and light pole with a single arm, and then a short and heavy, medium and heavy, and a tall and heavy pole with twin arms. So this is a pendulum test of the short and light and tall and heavy pole. Pendulum tests are very useful for some things. They're cost effective. Full-scale crash tests with vehicles are expensive. Vehicles aren't cheap. So a lot of times we'll go to pendulum testing for systems like this. And these can also be used to tune computer simulations, make sure that we're accurate. So for that example, the model pretty well captured the behavior of the pendulum test. So we move on to full-scale crash testing after that. So to start, we did MASH testing designation 360, so that's a 19 mile per hour test with a small car at 0 degrees, and it's impacting at the center of the vehicle. So computer simulation versus test. So with the simulation, the bottom of the pole gets out and away from the front of the vehicle, whereas with the full-scale crash test, that pole is still kind of just barely leading the front of the vehicle. Overall, the behavior isn't bad, but you do see that at the end of the simulation, the bottom of the pole is way up in the air, and with the full-scale crash test, it's going to come up a little bit, and then it's going to come back down. So even something as simple as a pole can be very difficult to capture in simulation. So this was a pass. I forgot to say that was the short heavy pole. This one is the medium heavy pole. And again, you can kind of see the bottom of the pole is kind of getting out a little bit ahead of the vehicle in the simulation. With the full-scale crash test, it isn't. And you'll see here, the bottom of the pole kind of digs into the soil a little bit. We do not model soil in this particular system. So it does kind of skid across the ground in the simulation, but it can't gouge into anything. But overall, the behavior was pretty similar. There was one other thing I wanted to say. Oh, you can see that this back windshield did break, back window broke, but because there was no penetration, this also passed. So that's all I have.